Okay, so now I've got three formulas for you in terms of summing either an arithmetic sequence or a geometric sequence. So let's look at the formula for an arithmetic sequence. The formula looks like this. I have to take, in order to find the sum of n terms, like n is the number of terms you're adding. So if you're adding 52 terms, then S sub 52, which would mean the sum of the first 52 terms. So n in that case would be 52. And you're going to do n times the quantity a sub 1, which is the first term, plus a sub n. Well, if n was 52, then you would need to know the 52nd term and add it to the first term. And then you can multiply by 52 and then finally divide the whole thing by 2. Got it? Okay. Let's look at summing a finite geometric sequence. Here's our formula. Very important. R can't be 1, because if R is 1, my denominator blows up. So that doesn't do me any good whatsoever. Okay? Same thing, S sub n. N is the number of terms that we're actually adding. Okay? A sub 1 is term number 1. R is the common ratio. And n is the number of terms you're adding. Now, I can also sum an infinite geometric sequence. And this one sounds a little nutty because you're like, how can you sum an infinite geometric sequence? That doesn't make any sense to me. Well, you know, the formula for summing an infinite geometric sequence is quite simple. I take the first term and divide it by 1 minus r. And you're like, okay, well, you know, that's a lot simpler, but here's what's the important part. The absolute value of your common ratio must be less than 1. That is the reason I can sum an infinite geometric sequence. Because think about it. If your common ratio is less than 1, then as you keep going out to infinity, do the numbers get larger or smaller? Yeah, they get smaller. And eventually they get so small that they eventually look like they actually become a 0 when you turn them into a decimal, right? Which is why at one point it looks like you're basically adding 0, which is why I can sum an infinite geometric sequence. Because as I keep going out, the numbers keep getting smaller and smaller and smaller until eventually these fractions look like they're zeros. Hang in there. I got some examples for us of summing arithmetic and geometric sequence. Okay, so let's take a look at these directions. They want us to find the sum. And they've given us two problems to work with. Let's look at the first one. It asks us to find the sum, S sub 20. What does S sub 20 mean? Yeah, find the sum of the first 20 terms of this particular series. Remember, a series is the sum of a sequence. Okay, well, what do you think you got to know first? You've got to know if it's arithmetic or geometric. So you figure it out. I'll wait. Go ahead. Let me know when you're done. Good. You figure it out? All right. So I've got this as an arithmetic sequence. I hope you do too. This arithmetic sequence has the first term as being 5. It has the common difference of being a positive 3, right? And I know I'm summing the first 20 terms. Does that make sense? Okay, so now here's the deal. The formula tells me to find the sum of the first 20 terms. I have got to do n, which is 20, and multiply it by the parentheses of a sub 1 plus a sub 20, and then divide it by 2, right? Okay, do I have all the pieces to my puzzle? No, I don't. I don't have the a sub 20, do I? Okay, so I need the 20th term. I got the first term of 5, but I don't have the 20th term. So we need to find the 20th term. So, find a sub 20. How are we going to do it? Yeah, just like we've been doing it. The 20th term is going to equal the first term, which is what? 5. Add it to 19 times 3. So, a sub 20 is equal to, yeah, 62. Got it? All right. Which means this now looks like 20, and in the parentheses will be 5 plus 62 all divided by 2. Cool? Okay, I know your calculators are out, you're figuring this out, and after all is said and done, I ended up in this case with S sub 20 equaling 670. So when I take the first 20 terms of this particular arithmetic sequence and I add them up, I get 670. You can double check it if you like. And you're like, how do you double check it? Write the first 20 terms out of the sequence and add them up. Yeah, you're like, you're not doing that. I totally get it. I'm not going to do it either. I'm going to trust myself on here. Good? All right, let's look over here. They want us to find the sum of the first 7 terms. Excellent. And again, I need to know if this is an arithmetic or geometric sequence. Go ahead. You figure it out. I'll wait. Good, I heard you. What is it? Yeah, it's geometric. And this geometric sequence has the first term being 6, and it has the common ratio of being a positive 2, and I'm looking for the first 7 terms, right? Okay, so S sub 7 of a geometric sequence looks like the first term times 1 minus r to the power of n, which is 7, right? All over 1 minus r. Okay, what's a sub 1? 6. What's r? 2. So 2 to the power of 7 over 1 minus 2. Okay, so I know you guys are working this out, your calculator punching, be my guest. After all is said and done, after you did your calculator punching, hopefully you agree with me. And the first 7 terms of this geometric sequence is 762. Did we agree? Cool. Okay, hang in there. Got a couple more. Okay, so let's take a look at these 2 problems. The first one says find the sum of the infinite sum? Okay, if this is an infinite sum, then this has got to be what type of sequence? Yeah, it's got to be a geometric. So, I'm not even going to bother trying if it's arithmetic, but I am going to confirm if it's geometric. Because if it's not geometric, then it doesn't matter. I can't find the sum. So, I'm going to confirm that it's geometric. You're like, how are you going to do that? I'm going to find the common ratio. So remember, the first term times that common ratio must be equal to 3, which means the common ratio must be this fraction 3/7. Okay, so if I take the first term of 7 and multiply it by 3/7, I get 3. Well, that's term number 2, so we're good, right? If I take the second term of 3 and multiply by 3/7, that gives me 9/7, doesn't it? Aha! I got the third term. We're good. Yay! So this is definitely a geometric sequence, and my common ratio is 3/7. Right? Okay. Now, oh, and the a sub 1, sorry, can't forget a sub 1 is 7, right? Now, go back and look at the formula we wrote down for the infinite sum of a geometric sequence. There was something I said was very important in order to use that formula. What was it? Yeah, the common ratio. The absolute value of the common ratio had to be less than 1. Is this common ratio, if I take the absolute value of it, is it less than 1? Yes, it is, which means I can find the sum of this particular geometric sequence. So, the infinite sum is going to be a sub 1, 7, divided by 1 minus 3/7, right? Okay, so 7 divided by 4/7, and we are going to multiply by the reciprocal, which means this infinite sum is 49 over 4, which is equal, if I needed it to write it this way, what? That's 12 1/4, isn't it? Right? And you're like, why is that again? How can you say that? Okay. Remember, the next one after this, I would have to multiply by 3/7. So what's 9 over 7 times 3 over 7? Yeah, that's going to be 27 over 49. This term multiplied by 3/7. Yeah, 81 over 343. The next one multiplied by 3/7. 243 over, what is that? 21, 2, 0. That's right. Do you notice how these fractions keep getting smaller and smaller and smaller? Right? Till eventually, when you turn them into decimals, they eventually look like they're going to be 0. Got it? Okay. Now, interestingly enough, 49 over 4 is not the exact sum of this geometric sequence. How can it be the exact sum of an infinite geometric sequence? What we say in this case, and I'm going to get rid of the 12 1/4 because I don't really need it. I just wanted to show you what that answer looked like. What we say is that the sum of this infinite sequence is going to converge to the 49 over 4 or 12 1/4. It's going to converge to that. It's not going to be exactly that, but it's going to converge. That's where it's going. Cool? Okay, let's look at this fourth one. Same question. They're asking me to find the sum of the infinite sequence. And the only sequence I can find the infinite sum of is geometric. So I have to confirm that it's a geometric sequence. So, again, first term times a common ratio needs to equal the second term. So 5 would be my common ratio. 8 times 5 is 40, right? 40 times 5 is 200, right? So confirm, definitely geometric sequence. But is this R correct? Yeah, no, because the formula says you need the absolute value of R to be less than 1. This truly is not less than 1. You're like, so? Hang in there. Okay, after 200 would be what? 5 times 200, this would be 1,000. Agreed? All right, etc. Right? Okay. If I tried finding this sum, so just bear with me. If I tried finding this sum, I would take the first term, which is 8, and divide it by 1 minus r, right? That would be 8 divided by -4. The sum of this infinite sequence would be -2, wouldn't it? Seriously? 8 by itself. 8 plus 40 is 48, not -2. All these numbers are positive and they're growing still. How am I going to get -2? That's why this piece of information is extremely important when you're trying to find the sum of an infinite geometric sequence. We say in this case, since the common ratio didn't cooperate, we say that this sum diverges. It ain't going where it's supposed to go. There's no way I'm going to be able to sum an infinite geometric sequence if that common ratio is not less than 1. Cool? Okay, hang in there. Got some stories for us.